Hi there, this is Courtney and Emmy, and this is our presentation on Introduction to Simulation. So first, we are going to define the three different types of simulation that we've covered, and it's discrete, event, continuous, and Monte Carlo. So discrete, basically we're looking at a system of ordered sequences that come in as well-defined events, and continuous is a simulation where the variables change in a continuous way, and then Monte Carlo is typically looking at the probability of different outcomes in a problem that typically can't be solved. It's really hard to solve mathematically or analytically, and they are typically just predictions or approximations. So for the first type, we have the discrete event simulation. So we already went over the definition of that, but basically all of these discrete event simulations must include these things over here. So a predetermined starting and ending points, the method of tracking the time that's elapsed, a list of events that have occurred since the process began, and then ones that are going to occur, and then some type of graphical, statistical, or tabular record of the function. The common applications of this are used in stress testing, evaluation of potential financial investments, modeling procedures, processes, and typically used in manufacturing or healthcare. So for our example, we're looking at the air traffic at an airport, and for here, our discrete events are the aircraft arrival, landing, and departure times. And here we can see the time that it begins and the time that we're going to end our simulation, and then we see that all the unprocessed events are stored in this pending list. So it covers all those bases that a discrete event simulation needs.
All right, so continuous simulation is a little bit different than discrete event simulation. And the main difference you're going to find is that continuous simulation is where state variables change in a continuous way. In other words, there's not an abrupt jump from one state to another, which means there's an infinite number of states, really. And continuous simulations can be applied to represent discrete phenomena as well. You can look at, for example, sales of products over time. If you want to look at how many shirts get sold over time, even though you take that as a discrete event, so you sell 5, 10, 15, 20 shirts, you can still look at it over time and get a continuous number or a continuous simulation or continuous prediction on it, which is an example of how you can use really discrete events with continuous simulation. And some of the common applications for continuous simulation are commercial flight simulators, gaming systems like the Wii, jet plane autopilot systems, and hydrogen bomb dynamics. So here's an example for a continuous simulation. So on the left you'll see a schematic, and that's just a simple schematic of a depletion mode transistor acting as a pull-up for a capacitive load. And with that schematic on the left, you'll see that we know the behavior of the components on that schematic. So what we're able to do is run multiple simulations and get a behavior of the system itself. So what you'll see is, after a while, it becomes a steady state system, and it's based on the formulation that we have in that graph under the behavior systems. So that's one example of how a continuous simulation is used. So now to Monte Carlo simulation. Monte Carlo simulations are used to model the probability of different outcomes in a process that cannot be easily solved analytically, and it must be predicted through simulation due to intervention of random variables. Basically what that means is when it's too complex to solve analytically, we try to use simulations to predict a solution. So this fits very well in business and finance specifically, especially like in things like stock markets, and especially business where it's faced with significant uncertainty, and there's better than a single average number. It's much better than a single average number itself when you use a simulation. Also, it's really great when systems are plagued by numerous random variables. So some of the common applications you'll see is asset price movement, informing investment and business decisions, assess and optimize computer network and performance. So there's some really great applications for it, and especially in places where you have significant uncertainty. So let's look at a Monte Carlo example. This is a really fairly often used example when it comes to integration. So in this example, we'll show that using a Monte Carlo method based on 1,000 random standard normal deviations to find a 95% confidence interval for the integral from negative infinity to infinity of e to the negative x squared times the absolute value of cosine of x dx. So as you can see on the right, you use that to actually manipulate the existing integral to pull out a distribution, and that pulling out of the distribution is called factoring a distribution. And as you can see, you can factor out a normal distribution from that integral. And then once you factored it out and simplified it, you get an expected value. So you get the bottom answer here, which is a square root of pi times the expected value of cosine of y over square root of 2. And in this way, you can now simulate these expected values over a distribution and then get your prediction on what this will be from negative infinity to positive infinity. So let's look at a bit of the history of Monte Carlo itself. It was kind of started through Stanislaw Ulam, who was a mathematician, or the originator, and he developed the Monte Carlo principles from assessing the game of solitaire. This was around World War II, and once he started kind of messing with the idea of the Monte Carlo principles, which they think was named after the gambling place where I believe his uncle liked to go gamble, he ended up bringing in John van Neumann, who worked with Ulam on developing a solution together. So when they refined it, they were actually refining it to use it on the Manhattan Project during World War II. And what they were doing with it was trying to investigate the properties of neutron travel through radiation shielding. And again, like I said, it was named after a gambling hotspot in Monaco with games of chance and random outcomes. So what are the differences between Monte Carlo and the other simulations we talked about? Well, clearly discrete event simulations are used to distinct state variables that model well-defined events, and we've talked about. Continuous simulations differ because they use continuous state variables as opposed to the discrete ones. And you can use in things like product sales, as we've shown before. Now, Monte Carlo uses these pseudo-random number generations to run simulations and predict outcomes. Again, it's kind of like we use our expected values of the example that we used for the integration, and it fares much better in instances where factors are non-probabilistic than discrete and continuous. So if there are any questions, let us know. Thank you.